So we have obtained the following metric tensor whose matrix expression is as follows. It is diagonal, and its components are e to the power of nu minus e to the power of lambda minus r squared minus r squared sine squared theta. So this is 4x4 matrix whose components are like this. Then non-zero components of the Christoffel symbols are like this: 1, 1, 1, lambda prime over 2, gamma 0, 1, 0, nu prime over 2, then gamma 2, 3, 3 equals to minus sine theta cosine theta, then gamma 0, 1, 1 is equal to lambda dot over 2 to the power of lambda minus nu, gamma 1, 2, 2 is equal to minus r to the power of exponent minus lambda, gamma 1, 0, 0 is equal to nu prime over 2 exponent nu minus lambda, and gamma 2, 1, 2 equals to gamma 3, 1, 3 is equal to 1 over r, and gamma 3, 2, 3 is equal to cotangents of theta, then gamma 0, 0, 0 is nu dot over 2, gamma 1, 1, 0 is lambda dot over 2, and finally gamma 1, 3, 3 is equal to minus r sine squared theta theta exponent of minus lambda. So all non-zero components of the tensor gamma mu nu alpha are written here or obtained from these guys with the use of the symmetry of this guy. All the rest of the components which do not follow from these expressions via this symmetry, application of this symmetry, are equal to 0. So this is prime, and prime means differentiation with respect to d, partial differential over d over dr, while dot means partial differential with respect to d over dt. So this is dot, this is dot, this is prime, this is prime. Here is dot. What else? Yeah. That's it to understand what is standing for the Christoffel symbols. So, to move further and for future convenience, for the future lectures, instead of writing this form of Einstein equations, let us write it in the form as if there is a non-zero energy momentum tensor. So we will write it in this form, r mu nu. Actually, we will write it in this, r mu nu minus 1/2 delta mu nu r equals to 4 pi kappa t mu nu. So we'll write in this form. In this form, for the metric under consideration, Einstein equations look like, actually, it should be probably 8 pi. Anyway, so 8 pi kappa t1 equals to minus exponent of minus lambda nu prime over r plus 1/2 plus 1 over r squared, 1 over r squared plus 1 over r squared. Then there are two equations, 8 pi kappa t22 is equal, this is the same, two equations of the same form, 8 pi kappa t33 is equal to minus half exponent of minus lambda nu double prime plus nu prime squared over 2 plus nu prime minus lambda prime over 2 minus nu prime times lambda prime over 2. Here is over r, sorry, over r rather than 2. Over 2 plus 1/2 exponent of nu multiplied by lambda double dot plus lambda dot squared over 2 minus lambda dot times nu dot over 2. And few more equations. Then we have equation 8 pi kappa t00 equals to minus exponent of minus lambda 1 over r squared minus lambda prime over r plus 1 over r squared. And the last equation 8 pi kappa t01 is equal to minus exponent of minus lambda times lambda dot over r. So we have written these equations as if t mu nu is not zero. T mu nu is not zero. The other part of Einstein equations, for example, corresponding to t13 or t12 or other components of mu nu, for the other values of mu nu, the other equations are trivially satisfied, meaning just that they have a relation something like 0 equals to 0. If the corresponding components of energy momentum tensor are 0. So if we put the other components of energy momentum tensor to 0, the other components of Einstein equations are trivially satisfied, like this. So now, having written Einstein equations in this form for the given ansatz for the metric, we continue with the consideration of the case when t mu nu equals to 0. So when this is 0, these equations are reduced to exponent of minus lambda nu prime over r plus 1 over r squared minus 1 over r squared equals to 0. So this reduces this equation. Then we have equation exponent to minus lambda prime divided by r minus 1 over r squared plus 1 over r squared equals to 0. So this form reduces this equation. And finally, this equation gives us lambda dot equals to 0. So this is the equations we obtain for the metric ansatz, for the given form of the metric from Einstein equations. So let me just stress one thing. Immediately one can see that nu equals to 0 and lambda equals to 0 solves this equation, just straightforwardly. Then the metric for this case reduces to the following form, which is nothing but the flat metric in Minkowski space-time written in spherical coordinates for the spatial sections. So nothing else. Now we want to look for a non-trivial solution of these equations. So we have obtained for the metric of the form RT dt squared minus lambda RT dr squared minus r squared d omega squared, we have obtained the following equations. Nu prime divided by r plus 1 over r squared minus 1 over r squared equals to 0, minus lambda prime divided by r minus 1 over r squared plus 1 over r squared equals to 0, and lambda dot equals to 0. And I forgot to say that those length equations, which were corresponding to T22 and T33 components, those length equations which were written on the previous version of the blackboard, these equations follow from this ones. So if these are satisfied, this satisfied also. Now we're gonna solve this find non-trivial solution of these equations. Non-trivial solution of these equations. And it is not hard to see that if we sum these two equations, if we take a sum of these two equations, we obtain that nu prime plus lambda prime is equals to 0. It means, because this is differential with respect to d over dr, it means that nu plus lambda can be function of time only, some function of time. But remember that we have a remaining symmetry that nu is changed to nu bar, remaining symmetry which respects this form of the metric, that nu bar plus log of dt over dt bar squared. So using this symmetry, one can fix this function to be 0. Then, as a result, we obtain that nu is equals to minus lambda. And finally, using this relation, one can solve these equations to find that exponent of minus lambda is equal to exponent of nu and equals to 1 plus C2 over R, where C2 is unfixed, is not fixed from this equation, it's some integration constant whose physical meaning and concrete value we will find just in a moment. But let me stress at this point that if C2 is equals to 0, C2 equals to 0, in this case we have flat metric again, but if C2 is not equal to 0, then the metric under consideration has the following form: 1 plus C2 over R dt squared minus dr squared divided by 1 plus C2 over R minus R squared d omega squared. And if we take the limit, this metric is approximated, if we take the limit R goes to infinity, it goes again to the flat metric approximately, dr squared minus R squared d omega squared. So we have the following situation. We have a gravitating center at R equals to 0, and it creates spherically symmetric gravitational field. And as we go very far from this gravitational center, the influence of the gravitating center on the geometry becomes smaller and smaller, and eventually at asymptotic infinity, spatial infinity, at spatial infinity, we see flat space-time which is almost unaffected by the gravitating center, which is situated somewhere far away from you. So this is physically meaningful, and this observation will help us to find C2. But at this point, let me stress that space-times which have this form, this sort of behavior, are referred to as asymptotically flat, although the notion of asymptotic flatness is a bit more complicated and goes beyond the scope of our course. So we are not going to discuss it in greater detail. So far, we just consider this as a definition, that if a metric goes to flat space-time as asymptotic spatial infinity, we consider this as asymptotically flat space. And now what we encounter is very interesting situation, that if we consider a spherically symmetric metric, in the case that T mu nu equals to 0 and lambda equals to 0, so in the case when these two quantities are 0, metric is spherically symmetric and goes to flat 1 at spatial infinity, then this metric is necessarily static. Static means that it doesn't change under the inversion of time and under time translations. It doesn't change. This metric is referred to static. So this is the essence of Birkhoff's theorem. We didn't prove it here. We just hinted to this property of Einstein equations. But we will come back to this property many times in the coming lectures. But at this point, let me stress that this property is very similar to the thing that we encounter in Maxwell's theory, where spherically symmetric solution that goes to 0 at spatial infinity is also unique, and that is Coulomb potential. So in Maxwell's theory, we have analog of this situation, but in general theory of relativity, this Birkhoff theorem has deeper consequences, as we will see in upcoming lectures.